Okay, so this is pretty much a continuation of the content of my previous talk at the SI seminar. So there I introduced some concepts and some techniques for causal analysis of observational data. And since then, I made some progress about these techniques. I learned more, and most important, I went from the toy examples that I presented that time into something that is hopefully a little bit more interesting and more compelling, especially for this audience. And so in particular, I analyzed Google Code Jam data. So Google Code Jam is a large programming competition that was organized by Google for 20 years. I think it was actually 19 years, because the last edition was in 2022, but they skipped 1 year because of COVID. So I think it was like 19 editions. And I'm sure some of you have heard about it, or maybe they're familiar with that, and maybe they even competed in that. So it's a worldwide competition organized by Google. It's very large scale. It's mostly the classic kind of like algorithmic problem. So you have to write an algorithm or implementation. Is very efficient and solves, I don't know, analyze a bunch of data and so on. And there is a wide choice of programming languages. Essentially, Google prepared some kind of like virtual machines with a Unix system installed with a lot of compilers for a lot of different programming languages. And you could still use different programming languages. So you just needed to provide a build script that pulls the dependencies and so on. And it involves every edition involved thousands of participants, and there is essentially each participant submits their solution in form of a program with all the compilation scripts, and then this gets executed on Google servers. And there's a bunch of tests that are run, and so the more tests you pass, the more tests your submission passes, the better it is ranked. So correctness is the main criterion. And then if there are multiple participants who submit to submissions that have the same correctness, so they pass the same number of tests, then they use the time. So when you submit your solution as a time breaker, okay? There's a time window of typically 24 hours or more for submitting solution to each round and so on. So that's a rough idea. And we thought that this kind of data is particularly interesting to analyze some kind of like features of how programmers work. Because very often, you know, when you analyze data about programmers, we have like two extremes. On the one hand, we have controlled experiments. Those would be the ideal situation, but it's very hard to run large-scale controlled experiments, right? So typically you're limited to, you know, a bunch of students who volunteer, or maybe if you're in a company, and even the tasks that these develop are typically to be small scale, and it's hard to, you know, follow them over many different kinds of events. At the other extreme, of course, we have software repositories. Those are great because there's a huge amount of data. But there it's purely observational, right? So essentially you don't have any control. So you can just look at what's there and try to kind of find relations and other indirect observations. And so these kind of programming competitions are a bit of something that is a little bit in between. Of course, it's still not a fully controlled experiment, but at least there are some rules. There's a criterion to evaluate correctness. We also, I mean, all of the participants, they have to do the same thing. They have to solve exactly the same task. But there's still variability in terms of languages and so on. So I think it was an interesting playground in terms of data. So to be a little bit more precise, so after you clean up and get to the gist of it, essentially each data point in this data set has roughly these 5 pieces of information. So for every submission, we know a nickname, which is essentially a unique identifier of the programmer, so the participant who wrote that solution, which problem they solved, so the unique identifier for the challenges, so each round of competition has a different challenge and so on. Then the programming language they used for the submission, the size, I think it's in bytes of the submitted program, the source code of the submitted program, and then finally the rank, which is the how that particular submission fared compared to all other submissions in the same round. So rank 1 means that was the best, rank 2 means that was the second best, and so on, right? And remember, the rank is based on correctness, and when there are ties on correctness, then it's time of submission. So it incorporates into a piece of information. So as I said, there's a huge variety of programming languages in all the submissions, but of course, as you can imagine, the usual suspects are at the top. So this is the statistics for, I think, pretty much all of the data analyzed. There was not all of the 20 years of programming contests, but it was only 8 because after 8 years, they changed the way in which the data is accessible. It was not so easy to mine, but still a sizable chunk. So you see C++, Java and Python, the most widely used for tens of thousands of submissions. And then the next one is C#, that is already 1 order of magnitude less. And this is like the bottom. So there was 2 submissions in Smalltalk, 1 in Eiffel, and 1 in Whitespace, which is this esoteric fake programming language, right? So they tried everything, but of course, those are not very representative. So we decided to focus for this analysis on the top 3, both because there's way more information about those, and also because they're being used consistently throughout all editions and so on. So it was a good focus. And the key research question that we investigated on this data is the following. So how does using different programming languages relate to the participants' results in the contest? Okay, and there are 3 key parts of this research question. First of all, two qualifications really. So first of all, we didn't consider all participants. First, because it was very impractical. It's a colossal amount of data, and even if you analyze very simple statistical models, it takes weeks. So we focused on what we call experienced participants. So what does it mean? Essentially, we have a threshold on the number of editions and participation rounds that a person should take place in. So essentially, we don't want people who just participated once or twice and then they just gave up or they were disqualified immediately, right? So we selected that. However, after all of this analysis, I'm going to describe the analysis based on this data. However, we also did analysis with the more extensive set of participants, and most of the findings are still there pretty much. So there's still, of course, you dilute a little bit these experienced participants if you include too many people, and at some point then everything happens, but more or less the same trends are still there. Then the programming languages, as I said, we only consider these 3 programming languages, the most used, C++, Java, and Python. And finally, results means rank. So essentially how much the programming language affects is related to how well or how bad a participant does, or the submissions of a participant do. So maybe before we go on, because I'm going to kind of like answer this question in some way. So maybe show of hands, who thinks that C++ was the one that was more strongly associated with good results? Okay, so I think more roughly half of the room. And who thinks it was Java? Okay, not very popular. And what about Python? Okay, right. I think it's more or less a tie within C++ and Python. Interesting. So I'm not going to spoil you the answer, and we're going to see it a bit later, of course. Okay, so the first thing that we did was we fitted a fairly straightforward regression model on this data. So the idea is that the response variable, the outcome is the rank. And then this is just, okay, it's a negative binomial because it's essentially rank is an integer, a positive integer. And then negative binomial instead of a Poisson, simply because we want to have a separate parameter for the variance. And then this is just a linear term that incorporates all of the information that we have about each submission. So we have an intercept for the language, an intercept for each person, for each the identity of each participant, an intercept for the challenge, and then we also take a term that is proportional to the logarithm of the size. We take the logarithm simply because the size of the submissions change quite a bit, and so we just look at orders of magnitude. This is pretty standard. Again, the details are not super important. And so if we fit this model on the data, this is what we get. So these are the confidence interval for the intercept associated with each programming language. So for C++, Java, and Python, okay? So essentially, you have to look at these intervals, and you have to see if they are below or above 0. So below 0 means, so negative, it means that that programming language is associated with a lower rank. So it's a reduction of the rank, okay? So lower rank means better, okay? So that means that Python is associated with better ranks. So it seems that Python is associated with the programmers doing better in this context. Instead, the C++ it's wash because it's smack in the middle, so we don't really we cannot really say much. And instead, Java is associated with worse ranks. Okay. So that was the first step of the analysis. However, so and this is the main point of this talk is these are just so the ones shown here are just statistical association, right? So there is a lot of things that go on, right? So there are a lot of factors that affect the outcome variable, so the rank in this case. And ideally, we would like to isolate the effect of language because that's what the research question is about. So we would like to go from just observing these correlations in the model into something that is more like a filtered, unbiased estimate of the causal effect of language on rank, directly of language on rank. And so one way of doing it essentially is, first of all, we need to build this kind of qualitative model of the causal relations between the various variables. And so this is essentially, I'm going to build now a graph where I draw a line when it's plausible that there is a direct causal effect between one node and the other. Okay, so for instance, well, of course, we want to observe what's the magnitude of the causal relation between language and rank. So of course, we're going to need an arrow like that. So now I'm not justifying every single line, every single arrow that I add to this graph. I'm just arguing that they're plausible, and in fact, as part of the analysis, but now I don't want to, discuss all of the details. We also investigated other variants of this model where the arrows are laid out a bit differently and so on. And so we ended up with something that is more or less consistent. Another thing that is important to remember is that there are different causal models that are still equivalent in the sense that they lead to the same conclusion as far as this analysis is concerned. So even if you get a few arrows wrong, that's not necessarily a big deal, right? So, but then we say, okay, the language affects the size because maybe there are programming languages where that are intrinsically more concise, they lead to more concise code. The nickname affects the language in the sense that different people typically have different preferences in the programming language they want to use. So they don't just pick anyone. The nickname also affects size because different programming styles. So some people can write more concise code. They prize that. The challenge affects both the rank and the nickname. The rank in the sense that there are challenges that are intrinsically harder, and so they might shift their rank. And it also affects the nickname in the sense that a particular programmer may decide whether to participate in a particular competition round according to what the challenge is. So they look at the challenge and say, no, this is horrible. So or maybe, oh yeah, this is great. I'm looking for more like this. And finally, we also introduced in this model an observed variable. That's why I put a rectangle around it. Skill. So skill is something that is probably very relevant for determining some of these variables, but unfortunately we cannot measure directly, at least for the data we have available, right? And so we can still put it in the model and then see what consequences it has, right? And so here it's plausible that, for example, different people have different skills. Skill affect the size, and challenge affects skill, and skill affect rank. Again, I'm not saying that this is the only reasonable model. And in fact, we tried a few others, but we did manage to do some partial validation. So partial validation means, so you're never going to be able to completely, fully validate a causal model like this, because ultimately the information about causal relation is not in the data alone. This is a key observation. And so we cannot just compute the statistic of the data. But what you can do is you can derive some consequences. So based on this model, and see whether they are consistent with the data, right? And so we managed, in fact, to rule out a few different variants of the model because they were not consistent, and instead this is consistent. And there are a few other variants that are still consistent, so they are essentially equivalent. Okay, so what do we do with this? Well, now essentially we can apply some analysis techniques that are rely entirely on the structure of the graph. So if we trust the graph, at least to some degree, then we can use it to select variables to include in our regression model, so that we don't just get a correlation between language and rank, but we filter out only that arrow and we cancel out all of the effects of the other factor, okay? And how does it work? Well, essentially we have to do two things. So essentially we have to look at all of the paths on this graph that go from language to rank. And then there are essentially two main kinds of things that we have to do. First of all, we have to block confounders. What does it mean? So here I'm showing you a path in yellow, and you notice that it's not a directed path in the sense that the path from language to rank goes against the direction of some of these arrows. So what this means is that this is a non-causal path because the arrows denote causality. However, this is still a correlation path because correlations don't have a direction, right? So these are just relation between two variables. And so essentially what this means is that if in this particular case, if we don't include the nickname and challenge into our regression model, then the correlation that we observe between language and rank will also incorporate the effect of challenge and nickname, right? Indirectly, because it's not there. However, if we do include nickname and challenge, like we did in the statistical model, then those will block this confounding path. And so we will, because we will have separately an estimate for correlation of this thing here, separately an estimate for the correlation of this thing here, and then we will end up with just the remaining effect of language or rank, which is what we want to isolate, okay? So this is the first thing, blocking confounders. And again, here I'm just showing you an example, but then you have to do it systematically on every path of a similar kind. Then there are another kind of effect that we have to account for, and this is what is called the effect of colliders. So a collider is when there is, again, a path that goes from language to rank in this case. This is the new yellow path. And size, which is a node on this path, is a collider because there are two arrows that enter size. Okay, so when that happens, it means that if we do include size in our statistical model, then this spurious correlation that goes through this path will be included in the term or the estimate of language. So in other words, for nickname and challenge, the conclusion is make sure they are in your statistical model. For size, the conclusion is make sure it's not in your statistical model. Otherwise, you're not measuring, you're not isolating that causal effect. Okay, and now I can finally explain the silly title of this talk. So the LHC is not a Large Hadron Collider, but it's a language heft collider. So heft is like a synonym of size, and so in this case we have a collider that is size between language and that. Okay, so that was just a play. So colliders are something that are pretty unintuitive the first time you hear about it, because unintuitively it seems weird that we have to exclude the information from our model to get to a more precise estimate of something, right? Because one would say, okay, the more information I have, the better, right? However, there are, if you think of other examples of colliders, and this is a classic one, it's not mine, I took it from a paper by I think some biologists, I think it becomes very clear. So this is another example of collider. Think about an actor or an actress, okay? So success is a collider between how good they look and how talented they are. So what does it mean? It means that in general, I think it's plausible that an actor's talent and their good looks are kind of like independent. So there's no correlation between them, because it's just what the genetic lottery and also the hard work of learning to become a good actor has determined. However, if we condition on success, so if we fix, for example, the success, we only look, for example, at very successful actors who participated in blockbuster movies in Hollywood, then we will observe an inverse correlation between looks and talent, because if we condition on success, then it will appear as if the more an actor is talented, the less he or she is good looking, and vice versa. But this is not really because there is this effect. It's just a figment of our statistical model. So essentially, we are conditioning on success, and then we introduce this spurious correlation. So it's a correlation, but it's not a correlation that reflects a causal effect. Okay, so that's the intuition that I think is a little bit easier to understand that on the other side. Okay, so the conclusion is that if we want a model that more accurately estimates the effect of language, we need to get rid of that, and then we can keep everything else in the statistical model. Okay, so now let's go back and compute again the confidence intervals and see in particular how they look like without the term size. So now the previous one was in orange again. and this is the green ones. Okay, quite a big difference. Okay, so now C++ below 0. So the interpretation is as before. So that means the C++ is now has a causal effect associated with the better results in the context. Python above 0, so worse results, and the Java is it crosses 0, but it's kind of like heavily in the lower part. So kind of there is a bit of association in with better results, right? Still, okay. So this means that we ended up with two very different answers to the research question, and it's not that one is correct and the other one is incorrect, right? So it really depends what we wanna, how we wanna interpret the question. So what we wanna know. So if we only care about prediction, so what is the best statistical model to predict as accurately as possible, given this information that we have, the rank of a participant in the contest, then the answer is that we should use the model with size, and Python, for example, has this correlation with better results. So using Python is predictive of better results in the context, fixing everything else. But if we are interested in a different question, that is to say, if we want to estimate, isolate as accurately as possible the effect on language on the results in this context, then we should not include size in our model, and the results are the opposite. So this is to say that C++ is associated with better results and Python worse results. Okay. Now, you might be wondering, okay, this is really weird, because how is it possible that that I have such a big difference, almost opposite results in one way or another, right? And so, first of all, I should say that we've been quite lucky to hit this kind of phenomenon, because in many cases, the causal model and the causally consistent model and the purely statistical model tend to be consistent, right? So there's also evidence that this is often the case. However, sometimes it can happen that you have these kind of deviations. And in particular, in this case, what happens is that there's a fundamental issue here. That is to say that the absolute magnitude of the effect of the programming language seems to be very small. So it's the point is that regardless of how you measure the correlations, the language is not going to make a big difference, which doesn't mean that it's irrelevant, but it means that other factors trump the language. Okay, and this is another a visualization of this phenomenon. Here I'm using the model with all variables in, and then essentially I represented the I'm not going to details how I can got this statistic, but essentially these are all comparable on they're all effects on a comparable scale, right? So we can see the absolute magnitude compare one to the other. And so this is these three bands, these three color bands correspond to the three programming languages. What does it mean? It means that essentially, again, in our data set, if we go from the better programming language to the worst programming language, the best programming language to the worst programming language, at most we can change something like, I don't know, what is it, like maybe a unit on this scale, roughly, okay? And you also see that the three bands are kind of like, they have a lot of overlapping, so that means there's a lot of uncertainty over exactly which programming language is better than the other. However, if we look at the nickname, which was another variable, so the identity of the participants, so these are all of the estimates for the coefficients associated with each participant. So this means that if we go from the best participant, from the worst participant to the best participant, then we can have an effect that is roughly twice as big as the change in the programming language. And then if you look at the challenge, so with the association, the coefficient associated with each challenge, a different problem, again, we can go from the hardest to the easiest challenge. There's almost like more than 4 units on the same scale. And this is the regression line. The pink line is the regression line for the size, which also has a pretty big effect, a pretty big span. So the reason why we managed to find these pretty major differences in the conclusions to our research questions, depending on whether we accounted for causal confounders or we didn't, is because the programming language in particular is not a very is a term that doesn't have very strong effects in absolute terms. And so again, doesn't mean that they're irrelevant. It means that they tend to be, dwarfed by everything else that goes on. And so that's why it's much easier to tease them apart. All right, so that's it. So this is just a short summary of a paper that was accepted to them not long ago. So feel free to have a look at the details, and of course, I should also credit my co-authors. That's that when I talk about statistics and causality, I'm always working with my friends Richard and Robert. And yeah, so to sum up. So I showed you an analysis, actually two analyses of statistical analysis of data from the Google Code Jam competition. And so we wanted to figure out which programming languages were associated with better or worse results in the context. And we noticed that the result that we get, the answer we get to these questions change quite considerably according to whether we try to control for possible confounding effects of the causal relations, or we just go with the plain, more straightforward statistical model. And that's it. I'm happy to take any questions.